Now that we've established the basics of vector spaces and vector operators and reference frames and coordinate systems, we can start building on top of this and adding more useful tools. And the first thing that we're going to add are two new vector products. And it's important to point out that these are not part of the formal definition of vector space. These are additional things, new things. And so what we will introduce is a scalar dot product, which operates on two vectors and returns a scalar, and a vector cross product, which operates on two vectors and returns another vector. So let's take these two in turn. So the scalar dot product is geometrically defined as A dotted B will give you a scalar that is the product of the magnitudes of A and B times the cosine of the angle between them. And the key thing to remember here is it does not matter if the two vectors in space are not co-aligned. This is just talking about directions and magnitudes. So I can have these two vectors that are mapping between different points. And let's say this is going from A to B, and this is going from C to D. That's okay. A and C do not have to be co-located. I can still take the dot product between these two vectors. In my head, I just have to take the magnitude and direction of this and transfer it over here, such that it is now defined with an angle between them. And I will get the proper result. So there's no restriction on where these vectors actually are in Euclidean space. So again, A dotted with B, magnitude of A times magnitude of B times the cosine of the angle between them. This operation is going to be commutative. So A dot B is same as B dot A. And it is going to be distributive over vector addition. And so it is A dotted into the quantity B plus C for any triad of vectors A, B, and C is the same as A dotted into B plus A dotted into C. And again, it will be compatible with scalar multiplication so that XA dotted into YB is the same as product XY times A dotted into B. And again, you can see this is a scalar and this returns a scalar. So everything is consistent. So that's the formal mathematics of it. Now, this also has a very, very strict geometric interpretation, and that is of projection, right? The dot product for Euclidean vectors is a projection operator. What is projection? Projection is taking the part of one vector that is in the direction of another vector. And so here I have these two vectors, B and A. And if I study these rules, I can prove to myself that this part of the A vector is going to be B dotted into A hat in the A hat direction. So let's forget the A hat direction for a second. Let's just look at B dotted into A hat. This part of B that is a height down onto A is the projection of B onto A. And so this is what the dot product operator is doing. It is projecting, it's taking the piece of B that is in the A direction. And we understand that formally as being the right triangle, the base of the right triangle that we get when we draw the height from the tip of B down to A here. And the same thing is true A to B, right? You can either rotate this 90 degrees in your head or just draw this height this way. The part of A projected onto B is this piece of the B vector. It is A dotted into the B hat direction in the B hat direction. So that's the projection. So when we were talking about decomposing our vectors into components of a reference frame, we were projecting those vectors onto the three unit vectors defining that frame. And now we come to the vector cross product. And the vector cross product is a true binary operator. It operates on vectors A and B, and it returns another vector C. And it is formally defined A cross B as the magnitude of A times the magnitude of B times sine of the angle between them, so sine of theta, in the C hat direction. And the C hat direction is the direction that is orthogonal, that is at 90 degrees to both A and B. Unlike the dot product, the vector cross product is anti-commutative. So A cross B is negative B cross A. It is still distributive over vector addition. So A crossed with quantity B plus C is A cross B plus A cross C. And it is still compatible with scalar multiplication, such that YA cross B is the same as Y times the vector A cross B is the same as A crossed with the vector YB. Now, what is the geometric interpretation of the cross product? Well, the cross product helps you find the direction that is mutually orthogonal to both A and B, but it also has a magnitude. And its magnitude, this A, B, sine theta, you may recognize from geometry, is the area of the parallelogram formed by the two edges A and B. And so this shaded region here will have magnitude of A cross B. And the vector A cross B will be this magnitude in the c hat direction, in the direction that is orthogonal to this plane. This is incredibly useful because this folds back into our understanding of the Euclidean basis, of the reference frame. If I have a vector A that is perpendicular to the vector B, which we'll denote as A perp to B, two things happen. First, A dotted into B is 0. So this is the first diagnostic for orthogonality for perpendicular vectors. If A and B are mutually perpendicular, then their dot product will be 0. And secondly, A, the direction A hat, the direction B hat, and the direction A hat cross B hat, or equivalently the unit vector of A cross B, form a reference frame, right? And this is tied into what you may have been taught as the right-hand rule. Another way of thinking about this is this cross-product circle. If I follow these cross products in the counterclockwise direction, counterclockwise because that is our convention for positive rotations, as we'll see shortly, A crossed into B gives you A cross B, B crossed into A cross B gives you A, and so on. If I follow this in the clockwise direction, if I go backwards, I will get negative values. So A crossed into A cross B should give me negative B. B crossed into A will give me, as we've already established, negative A cross B, and so on. And so I personally find this more helpful than, waving my hand in the air in front of me, but your mileage may vary. Again, do what feels most comfortable and most natural for you. Do whatever helps you get to the right answer the fastest. And then we can mix and match these things. You can actually define a whole bunch of triple products. Here, I'm listing out the ones that we'll be coming back to most often. The first is the dot cross triple product. And so this gives us a scalar value. So it's a scalar triple product because B cross C gives us a vector, and then A dotted into that vector gives us a scalar. And these can be circularly permuted to give the exact same result. So A dotted into B cross C is the same thing as B dotted into C cross A, is the same thing as C dotted into A cross B. And then we can mix two cross products. And the parentheses here are very important. So it's very important to remember that this form is A crossed into the quantity B cross C. And the mnemonic for remembering this is A crossed B cross C is back minus cab, otherwise known as A dot C, projection of A into C in the B direction, minus A dot B in the C direction. So back minus cab is a really convenient way of remembering this relationship. And now let's introduce a completely new thing. And the new thing is a generalization of vectors. And we call the generalization of vectors tensors. Tensors can be many dimensional. They can describe many, many different kinds of things. And for our purposes, we really only need to go to what are known as rank 2 tensors, sometimes known as dyadics. And in order to define this, we need to define a new operator, the outer product. And whereas the dot product and the cross product had very, very clear geometric interpretations, the geometric interpretation of the outer product becomes a little bit more hazy, but you can think of it as dimensionality increasing. The dot product is an inner product. It's the opposite of the outer product. So it was dimensionality reducing. We took two vectors and we reduced them via the dot product to a scalar. The cross product is dimensionality preserving. We took two vectors and got back a vector. And now the outer product is dimensionality increasing. So I call these rank 2 tensors. In the literature, you will find, instead of rank, these called order 2 or even dimension 2. And there's a lot of arguments, formal and otherwise, about which is the best way of best terminology. And it all has to do with definitions of these things in other fields, in most particular linear algebra. So very frequently you will see this called order 2 and rank being reserved for a different tensor property. And I just want to tell you that it really doesn't matter. So when I say rank 2, understand that what I'm talking about is a dyadic, right? So we're going to define this dyadic or rank 2 tensor T as the outer product of A and B. And just as we could decompose A and B into weighted sums of unit vectors defining a reference frame, we can do the exact same thing for the tensor. Because the tensor is now inherently a two-dimensional quantity, dimensional in the sense of the relationships that it's encoding. It's still defined on a three-dimensional space. It is encoded via measure numbers that are in a square matrix, whose elements we will call Tij. So with the definition of a reference frame I that has mutually orthogonal unit vectors E1, E2, E3, I can write A as the weighted sum of some measure numbers AI in those three directions, E1, E2, E3, which means that each one of my AI measure numbers are Cartesian coordinates in the space and are given by the projection of A onto each of those three unit vectors. So A sub I scalar is my A vector dotted into E sub I hat. And the exact same thing is true for B. And the exact same thing is true now for my tensor T, except it has a basis of the outer product of pairs of EI and EJ. And the way that we get back to those measure numbers, the elements of this matrix defining the components of T with respect to frame I, is by dotting T with pairs of those unit vectors. And so Ti sub j is the same as AI times Bj, the measure numbers of A and B. The formal properties of the outer product are that it is distributive over addition. So A quantity A plus B outer product of C is the same as outer product AC plus the outer product of B of C. And the same is true for it's both right and left distributive, right? But the ordering matters. It's not commutative. It is compatible with scalar multiplication in much the same way that the vector cross product is. And it is associative. So A outer product B, outer product of C is the same as A outer product with B, outer product with C. So that was very abstract and formal. We can make things a little bit better by noting that every single one of these operators that we've discussed can be expressed if you are expressing your vector in components with respect to a particular frame as linear algebraic operations. And this is now the payoff. This is the utility to stacking these things like column matrices. So the representation of a vector A with respect to frame I are the three components in that frame whose measure numbers are A1, A2, A3, corresponding to the Cartesian coordinates associated with that particular frame. The same is true for B, and the same is true for our component representation of our dyadic T, which is now represented as a square matrix, 3 by 3, because these are all Euclidean vectors, and we're working on a Euclidean space. And as we've already noted, each of these elements is equal to combinations of products of the measure numbers of A and B, like so. A dotted into B, its component representation in I, is the transpose of this matrix times this matrix. And again, if you think about the dimensionality of this, these are all 3 by 1, and so its transpose is 1 by 3 times 3 by 1, and therefore the output of this is a 1 by 1 matrix, otherwise known as a scalar, which is exactly what you would expect from a dot product. The cross product is given by the cross product equivalent matrix, which is shown here. This is a skew symmetric matrix. You will recall that a skew symmetric matrix is a matrix whose transpose is equal to its own negative. And therefore, for the real numbers, it must mean that it has all zeros along the diagonal, because the transpose does not change diagonal. And so the only way to make this relationship true for real numbers is to make the diagonal all 0. And then the off diagonal elements are negatives of one another. You'll notice that there's a very specific pattern of negatives here. This is what is encoding our right-handed rule convention. The fact that we've defined this skew symmetric matrix with this set of negatives is how we get our right-handed rule convention into the math of this. So it's really key that these are where they are. The quantity A cross B, its components in frame I, will be given by the matrix multiplication of the skew symmetric cross product equivalent matrix of A, which is a 3 by 3 matrix, times just the normal representation of B. 3 by 3 times 3 by 1 gives you 3 by 1, and you get back a vector as expected. It's anti-commutative, and so the same thing will happen if I switch the ordering, and it'll be the same as negative A cross B. I can define a dot product between a vector and a tensor, and what will happen is it will be the transpose of the A vector times the matrix of representing the dyadic T, the whole thing transposed. T dotted into A is just going to be the straight matrix multiplication of this 3 by 3 vector matrix with this 3 by 1 matrix. And so you will notice that the dot product is dimensionality reducing, even in the case where you're mixing two different geometric objects. You started out with a vector, a rank 1 tensor, otherwise known as a vector, and a rank 2 tensor, otherwise known as a dyadic. You take their dot product, and what comes out is a rank 1 tensor. So this operation reduced the dimensionality by 1. Same thing. The cross product is still rank preserving, right? So A crossed into T, you will expect another dyadic, and that's what you get. You get the cross product equivalent matrix, which is 3 by 3 times the matrix representing T with respect to frame I. 3 by 3 times 3 by 3 gives you another 3 by 3. And very, very counterintuitively, even though you would expect there to be a negative here, if you crunch out the math of this, you'll see that the proper form of T cross A is just T A cross. And I encourage you all to investigate this and convince yourself that it's true. And finally, the actual operation is just a straight matrix multiplication, just like in the case of the dot product, except that the transpose is on the second vector. So A outer product B, its components with respect to frame I, will be A times B transpose. And so this is 3 by 1 times 1 by 3, and you get back 3 by 3 as expected. We can immediately use this to give ourselves a operator for the magnitude of a vector. So you'll recall the definition of a vector dot above itself is the magnitude of the product of the magnitude of the two vectors times the angle between them. Well, the angle between A and A is 0, cosine of 0 is 1, and so the dot product A dot A has to be the magnitude of A squared. If we now write this in component form, A dot A is A transpose A, and that means that if I do this out, I will get A1 squared plus A2 squared plus A3 squared. Therefore, the magnitude of A has to be the square root of this, and we get back our usual Euclidean relationship that you learned a long time ago, but it's nice to see that everything here is self-consistent and matches what you already know.